Hey everyone, welcome to the Digital Design Crash Course, where today we'll be trying to cover the number system aspect of the course. So today we'll be diving into the world of number systems, and by the end of this video, you'll have an idea of how to do conversions between one number system to another. We'll start with a really simple notation where we just learn what exactly is number system to begin with. So it's just a way to represent numbers or to quantify things. You've been using decimal your entire life. If you think about it, we use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we call it base 10 because it has 10 possible digits. When you write the number 365, what you're essentially saying is there are three hundreds, six tens, five ones. Basically, it's 300 plus 60 plus 5, which is basically a 365. And here's the thing, right? There's nothing magical about having 10 digits. We probably use base 10 because we have 10 fingers to begin with. Whereas your computers, on the other hand, they kind of don't have fingers. They have your electronic switches. They have the two states, which is on or off. Therefore, they use a completely different system entirely. Today, we'll learn four major number systems, which is your decimal, also known as base 10, used by humans, your binary, also known as base 2, it's what computers use internally, your octal, which is base 8, it's a shorthand system, your hexadecimal, which is a base 16, it's another shorthand, but it's super popular in programming. And more importantly, we'll learn how to convert between all of them. So we'll start off with learning about binary. It uses two digits, which is basically your 0 and 1. That's exactly why we call it base 2. And why exactly do you think it's a really popular choice when it comes to computers? Is because it's really simple to represent with electronics. Since 1 and 0 can be represented as your on, off, high voltage, low voltage, which is essentially just 5 volts or 0 volts. It can also be used to represent true or false. I'll show you exactly how your binary actually works. Each position in a binary number represents a power of 2. So basically, if you think about this, if a number is placed in this particular position or in this particular order, then it would basically mean you take that position, which is your 0, 1, 2, 3, 4, 5, 6, 7, 8, and like so on, and you would take that as the exponent of 2. So it would be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. And this is essentially the value of powers of 2 with respect to your position. Let's say I want to convert this particular binary value, which is 1011, into a decimal value. Then how exactly would I go about it? Is basically I would take up each of these digits and then multiply it with 2 raised to the position of that particular digit. So it would be 0, 1, 2, 3, and that would be the powers of my 2, in which I would be multiplying with the digit accordingly. And once I get all of those values, I would sum it up, and that would give me my decimal value. So this is just a much easier version to see all of it happening in one place. So as you can see, 1011 is 11 in its decimal equivalent. How exactly would you convert your decimal to your binary? So it's kind of called the division method, where you have I, which is your decimal value, to be converted to binary. So at each step, you're going to divide it by 2 until you reach 0. So let's say you have 25, divide by 2. Your quotient is 12, remainder is 1. Write the remainder separately, it will be useful coming forward. So next you take the quotient, again divide it by 2. Your answer again would remain 6 for your this step, and your remainder is 0. Similarly, follow until you reach 0, and once you get all the remainders written down like this, you just need to read it from upwards. So you really need to go from 1, 1, 0, 0, 1. So you need it to be read from bottom to up. So you need to go from here upwards. So your 25 binary equivalent is 11001, and you can verify it by multiplying digits according to its 2 raised to the position the position that it is in. So your rule of thumb includes divide by 2, write the remainder, repeat until you get 0 as your quotient, and you would read the remainders backwards. So now you need to learn how to do binary to decimal conversion. And it's so much easier to go from binary to decimal because you just need to know your powers of 2. So let's say I want to convert 101101 from binary to decimal. All I have to do is take 1 and multiply it with the particular place value that I would get with respect to 2 raised to the position that it's present in. So it would literally be 1 into 32, 0 into 16, 1 into 8, 1 into 4, 0 into 2, and 1 into 1. You take all of those values, you sum it up, and that would be your total. That is your 45 is your binary equivalent, your decimal equivalent of the particular binary number given. Pro tip, let's say you're in a hurry and you want to finish this as quick as possible. Wherever you see zeros, you can skip just computing that so you can save some time. So now let's get introduced to your octal system, which is a base 8 number system where it uses 0, 1, 2, 3, 4, 5, 6, 7 only. It does not use 8 or 9 because it requires only 8 digits, hence the name base 8. So it works really simple. All you need to do is the only change that happens between from your binary to your octal is that instead of 2 to the power your position, it would be 8 to the power of your position. Let's say I have 157, which is a number represented in your octal number system. I'll have to take 7 into 8 to the power 0, 5 into 8 to the power 1, 1 into 8 to the power 2. And take all of those values, sum it up, and I get the binary equivalent. Why exactly octal, if you ask? It's basically because it's kind of a convenient shorthand for binary. Each octal digit perfectly represents 3 binary digits, and this made it super popular in early computing, but hexadecimal kind of replaced it today. Now let's say that you want to convert decimal to octal. This is pretty straightforward. All you need to do is just again, it works in the same principle as converting a decimal to binary. We divide by 8, take the quotients of each step, move on to the next step, again divide by 8, and go on until you get 0. You write the remainders in order and then you read from the back. So it's basically you're going to go from the last remainder upwards. So it will be 2, 3, 4. So that's like your, so this is basically your octal equivalent of your 156, which is in decimal. If you want to verify it, you'll take up each of these digits, multiply it with 8 raised to its position, and sum it up to get the decimal equivalent. And if they match up, then your answer is correct. It's basically the same method, you're just using a different base. Instead of dividing it by 2, you're dividing it by 8. Let's say I want to convert from octal to decimal, right? Again, it's a really straightforward approach. All you have to do is multiply each of the digit into 8 to the power of its position and sum it up to get the decimal equivalent. So the formula is basically multiply each digit by its power of 8 and then add all up. Next up is hexadecimal. It's basically a base 16 system, which means that we need 16 digits, but we only worked with so far 0 to 9, which is just 10 digits. So where do I get the remaining? So we basically borrow letters. Each of these letters basically represent, A represents 10, B represents 11, so on, F represents 15. So now we have 16 digits available to us. And the remaining, that is like from 10 to 15, is represented by your letters A to F. Again, it works by the same principle. You would use your 16 as your base value when you're converting from decimal to hexadecimal and your hexadecimal to decimal. But the only thing that you'll have to do extra is remember that alphabets have certain place value, like as in have certain values, and you need to remember to change them accordingly. So let's say I have 2f, which is in hexadecimal format, and I need to convert it to decimal, right? So my f is basically just 15. I write it as it is, and my 2 will be 2 into 16 to the power 1, which is basically 32. So 32 plus 15 gives me 47, and that is my decimal equivalent. Now, why exactly hexadecimal and why exactly is it so popular? Because one digit represents exactly 4 binary digits. So this makes it a perfect choice for writing your memory addresses, color codes, and so much more. Let's say I want to convert my decimal to my hexadecimal. What I'll do is, again, it follows the same process. I'll take my decimal value, divide by 16, write down the quotient, use it to follow the same thing in my next step, and go on about until I get 0. And I'll have to make sure that I write my remainders in order. Let's say if my remainders are 14 and 15, I'll have to convert them into the respective letters and then again go from FE. That is, you have to go all the way to the bottom and then read upwards. If I have to verify, again, I'll take, so it's FE, right? So F is basically 15, E is basically 14, and then I'll multiply it with 16 raised to the position that it's present in and sum it up. And that gives me my decimal equivalent, which matches the initial decimal value that we started with. So again, remember that you need to convert whatever remainders come from 10 to 15 into your letter, that is your A, B, C, D, E, F. If you have to convert from hexadecimal to your decimal, then you'll have to first, let's say it's 1A3, convert it, first write down the number as it is. So it's going to be 3 into 16 to the power 0, which is just 3. So A is 10, right? So it will be 10 into 16 to the power 1. And then you're going to take 1 into 16 to the power 2, which is 256. And then you'll just sum it up. And there you have the decimal equivalent. And remember that if you see letters, remember to convert them into numbers. So let's say you have to convert something from binary to octal. I'll teach you a small shortcut that you can go about using. It's a really convenient way to convert it. Let's say this is the binary number that you've been given. What you'll have to do is group it in threes, and that happens from your right side. So let's say I group this particular number in groups of three. I get 101, 110, and 110 again. Instead of converting this entire number into my octal form, what I'll do is I'll convert just these individual groups into my octal form and write it in order. And this time it's not from going from the end to the up number. It is as it is. So it'll be 566. So that is the octal equivalent of the binary number given. So now we'll just learn a small shortcut again to convert from binary to hexadecimal. It works really similar to what we did with respect to your octal, because it's the same process. Instead of grouping in terms of 3, we group in terms of 4. Let's say I have this particular number, right? Again, if I group it in terms of 4, it will be 1011 and 1011, and each of these will be respectively converted to each group. So this is just going to be taken in terms of the position, as in your 16 to the power of the position multiplied to the digit respectively, and then you have attained B and B. Again, you take it up as it is, and that would be your hexadecimal equivalent of your binary. Let's say I want to convert from my hexadecimal to my binary. What you'll do is you'll take each of your hexadecimal digit and convert it into your 4 binary digits. So your 3, even though like we've been learning it to be 011, we'll just add that extra 0 over here, because when it comes to 4 binary digits, you need to represent 3 also in terms of 4 binary digits. So it's going to be 0011 for 3, and F, as we know, it will be 1111. And this is a quick reference that you can use. Again, knowing it from 0 to 15 might be of like such a huge help when it comes to converting it from one number system to another. Now let's say I want to convert from octal to hexal. So that would literally use your binary as a bridge instead of converting directly from one number system to another. Let's say I have a number 157 that is in octal, and I want to convert it into my hexadecimal system. What I'll do is again take each of these digits, convert it into my 3-digit binary equivalent, and write it accordingly. After I write that result in binary, I'll group it in terms of 4 and then get my equivalent hexadecimal digit and write the final answer. So basically, if I want to convert from octal to my hexal, my binary will act as the bridge. Again, this is just everything put in one place. So if you have everything, let's say if you just know 0 to 4, honestly you can just repeat the same pattern again, because it's just going to be 0 0 0 1 1 0 1 1, and accordingly you'll do the same thing with zeros put over here and 1 put over here until you reach it 2 times, and the process just repeats every single time you add a new digit in the decimal system. So a quick summary, let's say if I want to convert from decimal to any of the system, I'll have to divide it by its base, I'll collect the reminders, and then I'll read it backwards. If I have to convert from any system to decimal, then I'll have to multiply that digit by its position and then add all the results that I have. The shortcuts that we've learned so far is basically if I have to convert from binary to octal, I'll group by 3. If I have to convert from binary to hexadecimal, I'll group by 4. If it's from octal to hexadecimal, then it's via the binary bridge. And now you've learned all the basic, as in the most important number system that we come across. So why exactly does it matter? Because every single time let's say you see a color code like this, and like let's say you see IP addresses or your memory address, every low level operation in programming, they all use these particular number systems. So you've just learned the fundamental of what exactly the computers use to communicate. So if you practice all of this, it'll really help you understand number systems better, and it might make it more easier to convert from one number system to another. So I'll see you in the next video. This is the end of the number system crash course.